Bismillahirrahmanirrahim. This is lecture number 20. Now we will discuss propagation of waves in monoclinic, orthotropic, trigonal, tetragonal and hexagonal. To start this, we will take the propagation vector n along x3 axis. This is what is written. This is written: propagation along directions linked to the crystal symmetry. Propagation vector n along the directions linked to the crystal symmetry. That direction of that this propagation vector n will be along that direction, which will be the symmetry axis of the crystal. That now we will link this propagation vector n with the symmetry axis of the crystal. And after making this link, we will study the waves in different type of materials. Suppose that our propagation vector n is along x3 axis. When it is along x3 axis, so it means n1, n2, 0, n3 is equal to 1. Then we have this gamma. Then our tensor gamma IL will be equal to CI33L. Gamma IL basically equal to gamma gamma L equal to CIJKL and JNK. Using there N1, N2, 0, N3 is equal to 1, we will be left only this thing CI33L. So with the help of this, we have components these. So when our propagation vector n is along x3 axis, then we have gamma in this form. These are the 9 components of this gamma. Now suppose that we have monoclinic material, and we know that in monoclinic material there is one A2 axis, and suppose that this x3 axis is parallel to A2, and we have also suppose that this A2 axis is parallel to x3 axis, and we have also supposed here that our propagation vector is along x3 axis, and for monoclinic material this x3 axis is the symmetry axis of material. So it means that we have made a link of propagation vector n with the symmetric axis, which is x3 here. That we have taken n along x3, and here x3 is symmetry axis. So when we have this, then as C34, C35, they are 0. So replace this C35, C3 and in C34, C35, 0 here. We have this. Now this is the matrix for propagation vector for this is the matrix for propagation tensor when we have monoclinic material. So it is this. So what we have to do, we have to find polarization vector of this gamma. And when we have polarization vector of this gamma, then we can define the waves propagating in this material. So first we will find the eigenvalues of this matrix. By finding the eigenvalues, we have lambda 1 C33, lambda 2 and lambda 3. From this, it would be equal to 0. It should be equal to 0. Lambda 2, lambda 3 will be this, and lambda 3. These are two eigenvalues, and this is the first eigenvalue. Now for first eigenvalue, we will find the eigenvector, which eigenvector of this gamma tensor, this propagation tensor, which is basically the polarization vector. If you go back to the previous lecture, you can see that the gamma IL PL equals to rho V square VL, PI. Where PI are the eigenvectors and they are basically the polarization vectors. No, P1 equals P1, first component, this superscript 1 is telling us that this is the vector corresponding to lambda 1, and these subscripts are telling that these are the components of this propagation vector, this polarization vector P1. So first component 0, second is also 0, third will be arbitrary. So you will choose that P3 will be equal to 1, that is unit. So this is the polarization vector. This is P1, first eigenvector. We have, and this is the propagation vector, this is the polarization vector, and you can see that these are parallel. So we have longitudinal wave. So what we have concluded with the help of first polarization vector of this gamma tensor, this propagation tensor, we have concluded that we have longitudinal wave with speed this speed. This is the rho V1 square eigenvalue, lambda 1 equals to rho V1 square, first eigenvalue. So V1 will be this, and this is the speed of a longitudinal wave in monoclinic material. Now other two waves will be transverse wave. In the theory we have seen that if we have one longitudinal wave, then other two will be transverse wave. Why they are transverse? Because the polarization vector eigenvectors are mutually perpendicular. When they are mutually perpendicular, then they will be perpendicular on the propagation vector n, because P1 is parallel to n. So P2, P3, when P2, P3 are perpendicular to P1, so they will also be perpendicular to the propagation vector, and then when they are perpendicular to the propagation vector and then we have transverse wave, and their speeds are, this is the speed, phase velocity, this is the phase velocity, lambda 3 rho speed, this is the speed of phase speed of transverse and transverse. Now if you have orthotropic material, and x3x is one of the symmetric axis of that orthotropic material, and if you remember that we have concluded there, when for orthotropic material some are zero, some are same with each other, because and it has less number of independent components as compared to monoclinic material. Why? Because it has more symmetry than in monoclinic material. So when we have more symmetry, then number of independent components will be decreased. So in that case our C45 is equal to 0. When C45 equals to 0, C45 equals to 0, then we have, where it is, C45 equal to 0, and then we have simply diagonal components are left. Here it is. Here we have diagonal components only. Simply use this in the monoclinic matrix of gamma. Matrix of gamma for monoclinic material. So when you will calculate the eigenvalues, you will have the result: lambda 1 C33, lambda 2 C44, lambda 3 C53, C55. See, again you have lambda 1 for C33 will be P1 this and this, so it means that you have longitudinal wave with speed this, and similarly other two waves will be transverse wave with speed this and this, and one is 0 1 0 0, another will be 0 1 0 as polarization vector, because one is longitudinal, the other two must be transverse with speed this and this in orthotropic material. So for monoclinic material we have one longitudinal and two transverse waves with speeds you have written there, and for orthotropic material we have again longitudinal wave with speed same as in the monoclinic material, and other two waves are transverse with speed v2 and v3. The speed of this wave will be different as in monoclinic material because it depends on eigenvalue here and here. Here we have only C44 and C5. There we have some expression for lambda 1, lambda 2 and lambda 3. That is why it can be different from here. Now for trigonal, tetragonal and hexagonal material. Now if you talk about the orthotropic, then I think these will be same, C44 and C44 and C5. They are the same. Now for trigonal, tetragonal and hexagonal material. And in these cases we know that our C55 and C544 are the same. So by putting this we have this type of gamma. This type of gamma. So lambda 1 is this, lambda 2, this is a repeating eigenvalue, C44. So for lambda 1 we have again longitudinal wave P1 and N. Then it means that other two waves will be transverse with speed C44 over rho. Speed for this longitudinal wave with obviously C33 or square root, whole square root, and inside the square root will be C33 over rho. Rho basically the density of the given material. These are the known things, and C33 is also known. These are the components of the elasticity matrix, and we know the components of elasticity matrix. This is given in the literature. Component of the elasticity matrix given in the literature. So we have longitudinal wave. So now for lambda 2 and lambda 3 we will find the eigenvector for this lambda 2 and we have lambda 2 and lambda 3. What are lambda 2 and lambda 3? They are C44. Now we will have to find, we know that the other wave will be transverse and speed of other wave will be this. We have to find only polarization vector. So for this type of eigenvalue we have this vector, and this vector will satisfy this type of equation always. This is our lambda, this is our vector equals to C44 again this, and we know that C4 is eigenvalue, so it means that this is the eigenvector. Any vector of this form will be the eigenvector of this tensor gamma corresponding to eigenvalue C44, and you can see that this eigenvector will lie in x1 x2 plane. So this is the polarization vector basically, and it is obvious that this must satisfy condition of unit vector, that alpha square plus beta square must be equal to 1, and third is 0, so it will lie in the x1 x2 plane. So any vector, any unit vector of the form in this plane is a polarization vector for C44. So our transverse wave with speed C44 over rho square root will propagate in direction n, having the polarization vector of this form in x, obviously it will be in x1 x2 plane. So here it is written, we have transverse wave with speed this C44 over rho and propagating along 001, n is 001, with any polarization in x1 x2 plane. And this polarization will be of form alpha beta 00, so then it must satisfy the condition for unit vector. Now by this we have a definition that which is acoustic. We have definition of an axis which is basically called acoustic axis. Such a direction along which a transverse wave propagate with any polarization is called an acoustic axis. That we are talking about a direction of a transverse wave in which a transverse wave that propagate with any polarization is called an acoustic axis. Here in our case, transverse wave is propagating with any polarization this, so we have defined this acoustic axis, that a direction along which a transverse wave propagate with any polarization is called an acoustic axis. Here we have that direction is x3 axis. Here we can see that along this direction our transverse wave is propagating with any polarization any polarization in this plane. So in this definition, with the help of this definition, our acoustic axis is this x3 axis. Now we have studied the waves, propagation of waves, that which type of wave will propagate in monoclinic material, orthotropic, tetragonal, trigonal and hexagonal material. from the start we have taken an our polarized propagation vector n with x3 axis. And our x3 axis is we have taken x3 axis as the symmetry axis in monoclinic, orthotropic, trigonal, hexagonal and tetragonal. No, we are left with isotropic material. No, we will study the which type of wave will propagate through isotropic material, and what would be the speed of that waves, those waves in isotropic material. In the next lecture we will see that how we will discuss that material with the help of this tensor, and how can we make use of this. That procedure of that will be different from here, as in finding the elasticity matrix of isotropic material we have adopted a different type of procedure. So similarly we will also follow a different type of procedure that will, I think, much easier than this. So first we will write the displacement equation for particular isotopic material. In generally we have calculated the equation of motion for displacement for any material, any continuum. So we will write that equation of motion for isotopic material. Then we will study that equation by supposing the solution again, and then we will simplify that. We will see that which type of wave will exist there, and with phase velocity, with what phase, with the phase velocity of that what would be the phase velocity of that wave which exists in the isotropic material. So it will be discussed in the next lecture. So thank you so much, and Allah Hafiz.